Hello guys, this is Rick from MathX, and today we're going to be recording another video. In this video, I've decided to go over 3 f is equal to ma problems, mainly because the exam's coming up really soon, and I'm feeling extra ambitious today. So without further ado, let's just get into these problems. First, an upright rod of length L is launched into the air with a vertical velocity v sub y. It is given enough angular momentum such that the rod rotates by an angle of 2 pi before landing. Find the initial velocity at the bottom of the rod. So, the first thing we should do is underline important parts of the problem. So, upright rod of length L, initial vertical velocity of v sub y, enough angular momentum to rotate by angle 2 pi, and find the initial horizontal velocity at the bottom of the rod. So let's think about this. So we know that in the entire motion, the rod rotates by 2 pi. And we're also given a vertical velocity v sub y. So it'd be in our best interest to find out this entire time of motion and represent it in terms of v sub y and probably g. So that we can understand what the angular speed would need to be, and thus we'll be able to figure out what the horizontal velocity would need to be. So calculating for the time of flight, the rod would be at its apex when v sub y is equal to gt. Which means that it would take v sub y by g to get to the top, and thus the total time of flight is going to be 2 times v sub y by g, like that. So we know that in this total time of flight, the angular momentum would have it rotate by an angle of 2 pi. So since it says angular momentum, we know that the angular acceleration is not playing into a part of it. So we really only need to consider the angular speed, angular velocity. So in order for it to rotate by 2 pi, we can also write the equation, the angular velocity times t is equal to 2 pi. Now here's the deal. These two t's are the same. The t I solved in terms of v, y, and g is the same as this omega t equals 2 pi equation, right? Because it says that it completes this rotation as it's flying through the air. So the total flight of motion is also the total time when it's rotating. So we can honestly just substitute this value of t back into this equation. And furthermore, we can also get the initial horizontal velocity. Using the bridge equation, we can write that the angular velocity times r would be our vx horizontal component of velocity. So we can write omega is equal to vx by r. So substituting this back into this equation, we get vx by r times t, I'm gonna erase that, because we can substitute t back into it directly as well, times 2v sub y by g is equal to 2 pi. So then we just isolate vx, v sub x by itself, and we just use simple algebra steps here. We can cancel through by 2, and we get pi r g by v sub y. But here's the thing. there's no r in this original equation. So even though we used r in the initial bridge equation, we'll have to figure out what r in this case would mean. So in our horizontal rod, it says that it's rotating. So since it's rotating, it's really just circling around a center pivot. So the radius of rotation, the r, would be L by 2. As such. So we can substitute that L by 2 back into the equation where r was. And we get that v sub x is equal to pi L by 2 g by vy. Or vx is equal to pi lg by 2 v sub y. Which gives us answer choice B. So what do we do? Just a quick recap. We first try to calculate for its airtime using v sub y and g. And then we recognized that this airtime would also be the time it spent rotating. So we substituted this v sub yg into our rotational motion equation. Then we used the bridge formula to solve for our angular velocity as a function of v sub x and the radius, and then we acknowledge what the radius really means. And we just got an answer. This problem wasn't too difficult. You just have to keep your equation straight and really kind of visualize what's going on here. And doing that, it becomes a relatively easy problem to solve. So, on to the next problem. A hard disk is pushed into a launcher between the boards until the boards make contact with it, distance L from the hinges, and are open to an angle theta as shown in the figure. What is the minimum force necessary to hold the disk in position? So first, once again, let's underline important information. It's pushed into the launcher between the boards, and it makes contact with each board a distance L from the hinge and is open at an angle theta, as shown in the figure. What is the minimum force needed to hold the disk in its position? So, this is kind of like this is really a force analysis static equilibrium type of problem. So, just like every problem of this flavor, probably the most important step would be drawing a free body diagram. So let's do that. I'll do mine a little bit off to the side because the diagram is kind of small and I write kind of big, so I don't want to get the diagram too cluttered up and confusing. So that's going to be my point mass to represent the mass of M. So what are the forces that will act on M? Well, we know that each of the boards is exerting a torque on the mass, and that's literally shown in the diagram. But we can't really turn a torque into a force. We can't just use the torque. We have to convert it back to a force. So what is the bridge equation from forces to torque? Well, it's L cross F is equal to torque. Okay, now for the next problem. A hard disk is pushed into a launcher between the boards until the boards make contact with it a distance L from the hinge and are open to an angle theta as shown in the figure. What is the minimum force necessary to hold the disk in this position? So let's first underline the important information. A hard disk is pushed into a launcher. So it's not staying there on its own. It's forced into there. Between boards until they make contact with the distance L from the hinge and are open to an angle theta shown in the figure. What is the minimum force necessary to hold the disk in position? So this is pretty much a force analysis static kind of problem. So just like any other force problem, the first step would be drawing a free body diagram. So I'm going to do my free body diagram a little off the diagram so it doesn't get messed up. So yeah, here's the point mass to represent M, and we need to draw some forces. But here's the thing. There are no symbols for forces anywhere in this problem. The only thing it gives us is a torque. So we're going to have to convert this torque back into a force. So how do we do this? We just use the bridge equation between forces and torques. So that bridge equation is R cross F is equal to torque as such, right? So what is our R in this case? R is the distance from the pivot. Well, in this case, it's pivoting around this spring, which it clearly states to be a distance L. So we got L cross F is equal to torque. However, cross product really only makes a difference when the force is applied at an angle that's not 90 degrees. However, in this case, it's really clear that the force is going perpendicular upwards. So really, we can just write our force as torque by L. So that's a good thing to know. And as I already kind of drew here, we know that there's going to be a force upward as such. And we just computed for the magnitude of that force to be tau by L. Similarly, we can also realize that this board, the upper board, will exert a force of the same magnitude perpendicular to its contact. So facing down as such. And we know that each of these forces, which I'm going to label as F, has the same magnitude of tau by L. So we need to basically figure out what is the smallest force that would balance these two forces. And this is where this problem kind of just turns into a pure geometry type problem. So depending on which axis we take, this problem can be really complicated or really simple. So a cool trick that makes this problem really easy is to take the axis with respect to the line of symmetry. Doing that and dropping the perpendicular components of each force using this axis actually becomes really simple. First off, we can see doing that, the y components of each force will cancel out, and these x components will get doubled. So if we find the angles here, we can figure out what the force outward exerted would be in terms of our tau by L and some angle or some variant of theta. And we can use that information to figure out the minimum force necessary to hold it back in place. So drawing onto this diagram, we see that taking this axis of symmetry, our angle theta gets bisected into an angle of theta by 2. And then by componentizing the force perpendicular between the board and the hard disk, we essentially drop a perpendicular. So using basic geometry theorems, we get that this angle here between the board and the mass is also theta by 2. And yeah, this is just because of the property that when we drop an altitude from the right angle side of a right triangle, we just get another smaller similar right triangle, which yields the same angle. So essentially, though, that means that this x component is the opposite side when compositizing this force. So this x component will be F sine theta by 2. However, since both of the forces from both of the boards are contributing to this force, the net force pushing the disk out is 2F sine of theta by 2. So substituting back our tau by L value for F, we get that the net force exerted outwards would be 2 tau by L sine theta by 2. Like that. So if this is the net force exerted outwards, like the net force that results from these two boards, in order to hold the disc back in position, we just need a force of equal magnitude pushing back on it as such. And in order to cancel out this value, we need to have it have the exact same magnitude of this. So this just tells us that our answer is the same value. It's just 2 tau sine theta by 2 by L, or answer choice A. Now finally, number 18. Or let's recap this first. So what do we do in this problem? We first converted our torques into forces, and then we pretty much drew a free body diagram, which we then used to find out the net force due to the boards and figured out what force we need to apply to it to cancel out that net force exerted by the boards. So this was actually a very straightforward static equilibrium type of problem. And all you really need to do here is draw out forces, componentize them, and then just pick the sum of vectors. So it's a very standard bookkeeping type problem. So anyways, now to 18. The disk is removed and replaced with a pie-shaped wedge of the same mass. And by disk, it's referring to the disk from 17. So that the hinge is still initially held open at an angle theta, as shown in the following figure. When the wedge is suddenly released, what is the final speed as it exits the lodger? So, this problem's a little different. Instead of caring about forces, as the last problem did, it's worried about speed. And it wants to know the speed when the wedge is released. So pretty much the two boards kind of close in on it and it gets ejected out. So typically in these types of speed problems, there are two routes that you could go for the F is equal to ma exam. You could either look at energy, or you could look at acceleration, and then using time you get a velocity. In this case, we don't really have a time, so the acceleration route doesn't seem like the right way to go. But the energy analysis route looks a little bit more appealing. So we would know that work is force dot displacement. But in this case, we don't have a force, we have a torque. So using its rotational equivalent, it would make sense for work to be equal to torque, the angular replacement for force, times angular displacement, theta. And this work would cause the mass to have some kinetic energy. It's clear that when these clamps come down, the slice is just ejected out translationally. There's no rotational kinetic energy. So we can write this work is equal to KE translational. So doing that, we can use our work using torque and angular displacement, and we can set that equal to the kinetic energy formula, 1/2 mv squared. So then here, solving for v, we get v is equal to 2 tau theta by m, and then take the square root of that, right, because it's v squared, which gives us answer choice D. So this problem is actually surprisingly easy, right? It looks scary because we have this weird slice shape and we're trying to push it out. But if you just convert it to an energy equation, it's literally 3 steps. So it's a pretty free problem on the exam. Compared to our last problem, the last problem was a little bit more straightforward, but it had more steps and you have to be a lot more careful. And the problem before that was also the same way. This problem, you identify the topic, you solve the problem. So that just shows you have to be able to pick up these clues on what concepts to use, because physics is pretty big, right? And if you go with the wrong concept, you'll be stuck here trying this problem for hours. But if you can identify that it's work, energy, problem becomes so easy. So I just went over 3 problems today. The 15, 17, and 18 problems, and I hope that I explained them in a clear way that made sense. If you guys like this type of video format, please say so in the comments and give this video a like. But other than that, I don't think there's really anything to go over. So, guess see you in the next video, and I hope you enjoyed.